First of all, I'd like to give you an overview about the anatomy of the ear. So we have different parts in the hearing system, starting with the outer ear that collects the sound and guides the sound through the auricle or pinna into the ear canal. And from there, the sound waves excite the eardrum or the tympanic membrane. Since the acoustic impedance in air is different from the acoustic impedance in the inner ear, we have a transduction there from low impedance from the air into the middle ear, in which we have the three small bones, the malleus, the incus, and the stapes, and these three bones transfer the vibrations of the eardrum to the inner ear. There are diseases in which there is ossification of those bones in the inner ear that lead to stiffening of those joints, and therefore the sound is not transferred to the inner ear. The inner ear, filled with fluid, needs another transduction of the impedance from the middle ear to the inner ear, and the vibration of D, the stapes, is then transferred into the window and then into the cochlea. Besides the cochlea, on the right hand side, the F, we have three, let's say, slings there, which are the vestibular organ to find balance, and this is close to the ear. That means whatever is going on there might affect the other thing. All the nerves that are assembled or placed in the inner ear form then the cochlear nerve, part G, that transfers all the nervous signals then to higher structures in the brain, and those structures contribute to all those processes that we experience hearing. Sound enters the outer ear and the auditory canal, goes to the eardrum, and hammer, anvil, and stirrup transfer that to the window, and then this goes, that's the oval window, and then these vibrations are going upstream into the cochlea, while the vestibular nerve that merges upstream with the cochlear nerve is conducting those nerve information about balance. We have the Eustachian tube connecting the middle ear with the mouth region, and this is what you might have experienced when you start or land in an airplane, when you go swimming, that there is a pressure sometimes, or diving, there's a pressure in the ear that's experienced, and you have to swallow, or you should chew chewing gum, whatever, to open or to allow exchange of air and exchange of pressure there over the Eustachian tube. How does sound conduction work? And I hope you see now the laser pointer that I switched on here on the slide. Here on the eardrum, the vibrations of the sound are transferred into the vibrations of those three bones, and since they act as a lever, we have here a certain amplification and an impedance matching to the oval window. This fluid-filled channel or canal here in the scala vestibuli goes into the cochlea, and at the very tip of the cochlea here, that is now extended just schematically, this is called the helicotrema, the scala vestibuli is transferred in the scala tympani, so the sound waves that go upstream in the cochlea are transferred downstream, and this vibration can be then seen at the very end at the round window. That somehow modulate the transfer and the impedance matching from the outer ear in air, low impedance, to the middle ear and the inner ear here at the oval window, fluid filled, that is high impedance. This adjustment can be actively done, and you might have had experience that if you enter a room where you know that there is a lot of noise, that by knowing that and actively entering such a situation, the noise appears to be less loud than when it happens incidentally, just to the sound volume adjustment of that muscle, of that tensor tympani muscle. So how does the inner ear work? As already said, we have the scala vestibuli and the scala tympani that are connected over the helicotrema at the end of the cochlea, and we have the third region here, the scala media, and all the transduction from sound waves in the scala tympani and the scala vestibuli is performed over the so-called organ of Corti and the outer hair cells here, that is, well, pinkish, purplish. While we have those hair cells, and when sound comes, the tips of the hair cells are displaced, and by that generator potential is generated in the outer hair cells and then transferred onto the cochlear nerve fibers, where action potentials are generated, and then upstream the signals run to higher centers of hearing. Those so-called stereocilia, these endings like seaweed in water, and if a sound wave propagates, they bend to one side, and since there is a wave coming through one direction and coming back the other direction, there's a traveling wave where those cilia are bent in one direction and then in the other direction. Thereby energy is transferred to the inner hair cells, and calcium influx takes place, neurotransmitters are released and generate postsynaptically action potentials on the cochlear nerve cells. The numbers here are is the intracellular versus extracellular potential in those cells that one could measure. Scanning electron micrograph here of the stereocilia of the outer hair cells, and we have spring-gated ion channels, and activation of the tipped links here opens the ion channels and allows ions to flow into the cells, and thereby this results in the other end of the cell to release of neurotransmitters in the synaptic cleft as shown before. So the facts here in summary, the sound propagation, we have a kind of middle ear amplification. The leverage effect of the small bones leads to a 22 times higher pressure in the inner ear and an impedance matching that the sound of different frequencies can be well transferred into the inner ear. The cochlea is filled with two liquids, the perilymph, that's the extracellular fluid, and the endolymph with a high potassium concentration. The cochlea is about 22 millimeters long with 2.5 windings, and the amazing thing is that the size of the cochlea is already reached when a child is given birth. That means over our complete life the cochlea stays at the same size. The perilymph between the oval and the round window vibrates with an excitation frequency and transfers vibrations to the basilar membrane, and the basilar membrane then transfers the vibrations to the outer and inner hair cells. This basilar membrane changes its mechanical characteristics towards the helicotrema, that means to the tip, from thin to stiff and from thick to flexible, so that different properties of different frequencies along the cochlea are taken into consideration, and therefore every point in the cochlea has its own resonance frequency, meaning that the different spots along the cochlea correspond to different frequencies, and hair cells sitting there are then encoding those frequencies. That means we have a kind of acoustic Fourier transform all along the cochlea, and a lot of channels there that have a very narrow bandwidth and are coding for a certain frequency band. The basis, and the higher we get here, the lower the frequency is. That means the longer the wavelength. Hearing range is giving in sound pressure level, SPL in decibel. And we have here a lot of curves, and the question is, what do they show us? First of all, we have a pain threshold here of about 130 dB, and we have the normal hearing threshold that is below 10 dB. And here, if you are in rural areas and it's silence, then you have about 10 dB. Very low when you speak at a very low sound level. Then we have 100. Normal speech is 1000. Noise from the street about 10,000. Industrial noise about 100,000. Thunder or a shot is 1 million, and a jet engine is 10 millions. So that's the factor. Having the logarithm of the decibel unit, we come to those numbers here. And what do you see? Let's go to the level of everyday speech here, that green blob, and everything. And what we see is that here at 1 kilohertz and a frequency 1 kilohertz and a sound pressure level of 50 dB, to experience a frequency that is much lower, let's say here go down to 20 hertz, we need a much higher sound pressure level to experience that frequency at the same subjective loudness as at 1 kilohertz, and the same is true for higher frequencies. At about 8 kilohertz, the sensitivity is least or much lower than compared to 1 kilohertz. Another point that we see is that um, the the more silent it gets, the lower and the higher frequencies come together. So that means we have a very complex picture here of sensitivities in hearing. You should take it home that the loudness is in phone is referred as decibel at 1 kilohertz. So if you go to old units, this is very old unit here, and being in the youth, we are able to discriminate frequencies between 20 hertz and 20 kilohertz, highest sensitivity in the mid kilohertz range. The older you get, the lower that upper limit of perception of sound gets. And on the right hand side we see here the loudness level in phone. That means the dB sound pressure level at 1 kilohertz. And the pain threshold is about 130 here. And this damages the hair cells dramatically in the inner ear. Worldwide. In the year 2010, 10% of the population suffered from that, and numbers are increasing. On one hand, due to aging societies, on the other hand, due to listening to loud music, having in-ear earplugs and stuff like that. So we have on one hand age-related hearing loss by generation of the organ of Corti, but also associated with widespread diseases like diabetes that reduce blood flow in the inner ear and therefore also come or promote loss of hair cells. We might have developments over time due to hair cell degradation caused by permanent noise or toxic injuries of the inner ears by infections by pharmaceuticals or by toxins, and there's also another group that suffers from inherited defective hearing. Is what can we do? You would say, hey, let's take hearing aids. So, but what are challenges and requirements? If you have a hearing aid by yourself or somebody in your family using a hearing aid, you might have heard about that. First of all, you have to adjust the acoustic noise to the device. So bring the environmental noise in a range that amplification of that desired noise level or sound level is projected to the residual hearing. Adjustment of the device signal to the very specific personal particular ear. Of course, biocompatibility of the material. If you have an earplug in ear all day long, there is interaction with the skin, there is interaction with the air in there. You should prevent infections, so all the questions of biocompatibility. The device should be convenient and easy to handle, taking into consideration that elder persons might also have other impairments like suffering from rheumatic arthritis, suffering from gout, so your fingers get stiffer and therefore your eyes get worse. That means all the buttons, the wheels, the switches and the knobs should be large enough, and they should be placed in places where you can approach them. What you see here is a relatively new device with only a very small tube that leads into the ear and amplifies the signal close to the eardrum. Should have an aesthetic apparel and appeal that changes over time. In older days, things had to be like this color of skin, so between sand and khaki. Nowadays, metallic colors are really fashion. So this is really depending on the society in which you live and depending on the time where we are. The fixation is important. You want to walk, you want to move, you want to shake your head so it should not fall apart. And it should adapt to the hearing impairment. That means if you have changes over daytime, changes from day to day, there should be kind of auto calibration of an ear mold. And the newer ones don't have an ear mold, but a freely floating loudspeaker on tip. You have an ear hook that holds the behind the ear device in place, and in the behind the ear device you have a battery, you have a microphone, a speaker, and all of the electronics. That's shown here in a block diagram. So we have amplifiers. From the microphone we have an analog digital conversion, we have a digital signal processor, and at the outcome a digital to analog converter, another amplifier to drive the loudspeaker here. And this is really a very sophisticated system, and this body in the middle here, the digital signal processor, should be programmed such that it's energy efficient, that battery lasts at least for a whole day. And of course, this is not just a simple operational amplifier that amplifies everything, but has certain frequency bands, for example, to suppress very low frequencies that can be caused by vibrations or movements, so suppression of movement artifacts. You should not have any feedback loops and should keep the distortions as low as possible. Implanted hearing aids are the second one, and we have three different solutions. There are middle ear implant systems, as already said before, when you have ossification of the middle ear bones, so no longer movements between those three bones, but they get stiff and cannot act as an impedance matching system. And there have been approaches that you implant something that takes the outer sound, transfers that into a vibration of a transducer that puts an actuator on the oval window to create sound waves in the inner ear. We have a so-called bone conduction implant system with the idea that we do not receive sound only through the ear canal, but also through vibrations. You might have experienced that you have put your head somewhere and you experience the sound coming over the solid state materials. And we have cochlear implants where the transducers in the inner ear, the ciliary bodies of the hair cells, do no longer transduce the propagating sound wave information into electrical signals. Audio processor, mostly external, wireless transmittance of energy and information, that means data from the outside sound, implanted receiver, a cable here to the middle ear, and an electromechanical transducer. Might it be by a kind of electromagnet, might it be by a piezo transducer. As second, a bone conduction implant, and this is really as it seems to be here. So we either have a vibrational system completely, implanted here in the bone, and an external part being placed wirelessly with the help of a magnet to fix it to the inner part. There, as shown on the left-hand side, or the older version where you really have a percutaneous screw. Percutaneous means the outer part of the screw sticks through the skin out of the body, and you place your vibrational system on top of that. So, and last not least, the cochlear implant system. They look similar no matter from which company they come. This here is the implantable system, having a coil for wireless energy and data transmission, having an hermetic package with implantable electronics, having a magnet to connect to the outer coil shown here on the right hand side, and having an electrode array being placed inside the cochlear. We have the outer part of the transmission system, another coil with a counterpart for this magnet, and a connection to a behind the ear device, which carries batteries here in that shaft, which carries electronics and have a microphone to record the outside sound and transmit it then over this coil to the implant part that stimulates via those electrodes. This here is a remote control where you can change within the safe limits of the implant a little bit the volume, or you can change between one or two programs that have been personalized to you for different situations. Well, up to 600,000, but the numbers are not that clear. Or cochlear implants. The thing is that we have 16,000 hair cells in the inner ear. Just as a comparison, we have millions of rods and cones in the retina for vision. And that this is really the first successful replacement of sensory sense in the human body. We have gene defects, different autoimmune diseases, viral or bacterial inflammation, Meniere's disease, that's an inner ear disease, or people who lose their sound just by noise. And everything from the cochlea, that means the auditory nerve and all the structures towards the auditory cortex, must be intact that such a system works. We have direct stimulation of the nerve fibers sitting a little bit further distance from the cochlea, and it works for children and adults. We have 16,000 hair cells. We have a maximum of 22 electrodes. Here we go, another version from another company of that system here. This is the implant, having the coil with a magnet, having left to that number 10 the implant package with the electronics, having a curled electrode array number 9 that goes into the cochlea, and having as aid the reference electrode that is outside the cochlea, and I'll tell you later on what this reference electrode is good for. On the external part, we have the ear attachment with a microphone, processor unit, operating switch, display if it has one, control and transmitter coil. So, magnify the stimulation array, we see 22 platinum-based stimulation contacts. The package is made out of ceramics and titanium. This is now from Mid-L. Third company is Advanced Bionics, and Oticon, the fourth one, is also around. Encapsulation or overmold is made out of rubber. This is how it is implanted. The electronics is placed in a small hole that's ground into the temporal bone, and then a hole is drilled to enter the round window here, and the electrode is inserted into the cochlear. The cochlear electrode array does not reach the most apical turn of the cochlear. That means low frequencies are not possible, and this is a challenge because we need the low frequency components for the structure, so the consonants of the speech, and therefore you have to go as high as possible to get that structural clarity. And the perilymphatic fluid is highly conductive. That means even if you would have many electrodes and you would place them closely to each other, they might get short-circuited over that fluid of the scala tympani. So effectively, and nowadays, you can separate frequency channels about 8 or 9. And that means the preservation of the hearing, of the intact hearing, or the replacement is not fully achievable, and we still have to differentiate between normal speech and cochlear implant-based speech, even though programs with a computer, rehabilitation session learning, there is a lot of support, and people can cope very well, but everybody who has acquired hearing loss and reports tells you that there are differences in normal hearing and cochlear. It's relatively high, so we need a wideband frequency response, but blank out lower frequencies to suppress movement artifacts and vibrations, for example by walking or moving the hat. You want to increase the speech frequency responses and filter ambient noise, and you can imagine having children, males, females with different pitches, with different tones, so this is quite challenging, and even more challenging is to focus on speech. So the well-known cocktail party problem, that you really struggle a lot to listen to the right person there. You want to listen to instead of hearing all of those guys and girls talking between each other, and you just hear noise instead of sound. What can one do? There are directional microphones. So we have a kind of, if we have binaural hearing, so hearing with both ears, we can focus and tune somehow the direction in which we want to listen to. And this is now tried out with directional microphones, exploitation of interferences for noise cancelling, or positioning microphones in the ear canal to get that directional coding by the auricle. That means you slightly move your head, and you can resolve up to 1 degree of spatial angle with that. What else do we have to know? As this is part of an engineering course, have to bounce you back to transcutaneous connections here, and transcutaneous means over the skin. So how to transmit energy from the outside to the inside, and how to have bidirectional data exchange. We use inductive coupling here. That means we have an alternating voltage source outside here, a serial resonance with a resistor, a capacitor, and an inductor, and can tell you we go into that more in detail one of the last lectures of that course. And we have a coupling between the external part of the system and the implant system. In the implant we have a parallel resonance here, again inductor, capacitor, resistor, and the load, which is the stimulation electrode here. Reference electrode placed outside the cochlea. This could be either in the temporal muscle or on the receiver case. And if you carefully look here, you see that this part is open in the middle of the receiver case, and this could act as a counter electrode. Or you can stimulate one electrode on that front part electrode array versus another electrode. Or one electrode against all the others, which is called common ground. So typical pulse widths are between 10 and 400 microseconds. Currents can go up to the milliamp range, and frequencies are relatively high in cochlear implants, above 100 Hertz. This is how it looks like if we stimulate bipolar. We have a limited field, but if the nerve cell would be further distance, would be really hard to reach the nerve cell. With a common ground, we can somehow shape the electrical field to get directional asymmetries, and with a monopolar one, we have a very strong gradient around the electrode, but the current goes here through all the tissue in between to either the reference electrode or to a reference electrode on the surface of the package casing. So that was a wild rush through cochlear implants. I have to say this is only half of the story of cochlear implants. The other half of the story is in coding of the sound, in stimulation coding. This is an art of its own, and this goes far beyond the scope of this course, which mainly wants to focus on the miniaturized parts of devices. So results, just to finalize some information, results of your last test should be around. What comes next is lecture 4 and 5 and exercise 3, and this goes all in the next test on June 24th. Boundary conditions are again the same. Go to the Ilias system, download around noon, upload till 1 p.m. sharp. Don't forget your name on the pages. If you forget, don't worry too much. The system will print your name somewhere, since you have a personal login on the Ilias system. And just as here, forecast exercise 4 on July 1st, peripheral nerve interface. So that's all for today. Thank you very much. If you have questions, don't be shy, write them down on the question and answering section on the Ilias portal. If you want to have a more personal response, feel free to send it directly to me. Thank you very much, and hope that you listen to one of the next recordings soon. Bye-bye.